382. That is the number an automated seismic tracker just logged along a stretch of ocean floor most Americans have never thought about. 382 tremors quietly rippling through rock that sits 70 to 100 miles off the coastline of Washington, Oregon, and Northern California. A few weeks earlier, the count was 307. Before that, it was lower still. Nobody felt any of it. No dishes rattled, no sirens sounded. And yet, inside the offices of the Pacific Northwest Seismic Network, a very different kind of alarm has been going off. Not the kind you hear, but the kind you read in a rising line on a graph. This is not a story about an earthquake that has already happened. This is a story about a fault that is talking, in a language most of us were never taught to understand. Scientists have a name for that language. They call it episodic tremor and slip. And right now, along the length of the Cascadia Subduction Zone, that language is getting louder. Somewhere beneath the waves off Vancouver Island, down through the coastal waters of Washington and Oregon, and into the northern edge of California, two enormous slabs of the Earth's crust are locked in a slow, silent collision. The Juan de Fuca Plate is being forced underneath the North American Plate, inch by inch, year after year, at a pace of roughly 4 centimeters annually, about the speed your fingernails grow. Most of the time, that boundary is stuck. Friction holds it in place. Stress builds. And when that stress finally releases in one violent instant, the result is not a tremor. It is a megathrust earthquake, the most powerful category of earthquake our planet produces. The last time that happened here was the night of January 26th, 1700. There were no seismographs then, no satellites, no instruments of any kind along this coast. But the Earth remembers. Coastal forests sank several feet in an instant, drowned in salt water, leaving ghost forests of dead cedar that still stand today. A wall of water crossed the entire Pacific Ocean and slammed into the shore of Japan with enough force that Japanese scribes recorded it as an orphan tsunami. A wave with no earthquake attached, because the earthquake that caused it was on the other side of the world. It would take 3 centuries, and a small army of geologists comparing tree rings, sediment layers, and indigenous oral histories to finally connect that Japanese wave to a magnitude 9 rupture on a fault line most people had never heard of. That fault line is Cascadia, and it has been quiet, on the surface, ever since. But quiet does not mean inactive, it means the opposite, and that is exactly why scientists are watching the tremor count so closely right now. To understand why a rising number on a seismic chart matters, you first have to understand what tremor actually is, because it is not the same thing as an earthquake, and that distinction is the whole story. An earthquake is sudden, rock breaks, energy releases in seconds, and the ground shakes hard enough for you to feel it, sometimes hard enough to level a city. Tremor is nothing like that. It is a slow, weak, rolling signal that can last for days or even weeks, buried so deep in the noise of the planet that, for decades, seismologists filtered it out as background static, an error, something to be cleaned off the readout before the real data could be examined. That changed in the early 2000s, when researchers studying northern Cascadia noticed something strange. Every 13 to 14 months, GPS stations along the coast recorded the ground moving backward, the opposite direction of the normal, gradual crustal deformation caused by plate subduction. At the exact same time, buried in what everyone had assumed was meaningless noise, there was a matching pulse of low-frequency seismic chatter. The two phenomena were happening together over and over on a clockwork schedule. Scientists called it episodic tremor and slip, ETS for short, and it turned out to be one of the most important discoveries in subduction zone science in the last quarter century. Here's why it matters. Deep beneath Cascadia, below the locked, stuck portion of the fault where a future megathrust earthquake will originate, there is a transition zone. In that zone, the plate boundary does not stay frozen. It slips slowly and repeatedly, releasing built-up strain in small increments rather than one catastrophic event. As it slips, it generates the tremor. Think of it as the fault's way of exhaling. And scientists have proposed something that keeps them up at night. Those small, deep exhalations do not relieve stress on the shallow, locked portion of the fault, the part capable of producing a magnitude 9 earthquake. If anything, some studies suggest tremor and slip episodes may nudge additional stress upward onto the very section of Cascadia that has been silently loading since 1700. That is the reason 382 tremors is not just a number. It is a real-time transcript of stress moving through a fault line that has been building toward its next major rupture for over 300 years. For most of the last 2 decades, the story of Cascadia tremor was one of quiet, cyclical rhythm, a slow slip event roughly every 14 months in the north, somewhat more frequent and less predictable in the south. Scientists built entire monitoring careers around this metronome. But recent tremor catalogs are showing something that has caught the attention of seismologists across 3 states and 1 Canadian province. Activity that is not confined to isolated bursts anymore, but appears to be spreading and intensifying along nearly the entire length of the zone at once, from Vancouver Island down through Washington, Oregon, and into the northern reaches of California. In mid-May of this year, the Pacific Northwest Seismic Network's automated catalog registered 369 distinct low-frequency tremor events clustered along the southern portion of the subduction zone in a single reporting window. Weeks later, that number climbed to 382, and researchers noted the activity was no longer confined to one segment. It was appearing simultaneously across multiple sections of the 700-mile fault, from the Mendocino Triple Junction in the south to waters off British Columbia in the north. Southern Cascadia, historically the most tremor-active stretch of the zone, lit up first, but northern Cascadia, where the fault is capable of producing the largest magnitude events, has not stayed silent either. This is the part of the story where a documentary voice is tempted to reach for the word earthquake and stop there. But the honest answer is more complicated and more interesting than a simple countdown to disaster. A rising tremor count is not a prediction. Seismologists have been extremely clear about that. What it is, instead, is a live readout of stress redistributing itself across one of the most dangerous fault systems on Earth. And for the first time in the history of Cascadia monitoring, researchers have new tools capable of watching that process almost as it happens. That tool is called the Regional Cabled Array, and it may be the single most important scientific instrument most people have never heard of. Stretching more than 550 miles along the seafloor off the coast of Washington and Oregon, it is a web of fiber optic cable and precision sensors sitting directly on top of the Cascadia Subduction Zone, listening. Before this array existed, almost everything scientists knew about deep offshore tremor came from onshore seismometers, picking up faint, distorted echoes of activity happening dozens of miles out to sea. It was like trying to diagnose a patient's heartbeat by listening through a wall from the next room. The regional cabled array put the stethoscope directly on the patient's chest. Using data from that array, a team led by postdoctoral researcher Malene Kidawala at the University of Washington uncovered something that reframes the entire tremor conversation. Buried within episodic tremor and slip events, they found evidence of migrating fluid, hot water, laced with dissolved minerals and gases, forced upward through the fault as the plates grind past each other in slow motion. That fluid does not just sit there. It carves pathways through the rock. It weakens the fault from within. And according to Kidawala's research, it may be actively accelerating the mechanical breakdown of the plate boundary itself. In her words, the tremor and slip process is generating the very fluid highways that could be softening Cascadia's grip on itself, section by section, cycle by cycle. There is a reason this discovery landed as hard as it did within the seismology community. Cascadia has always been the strange outlier among the world's subduction zones. Compare it to Japan or Chile, and the difference is stark. Those faults produce frequent, felt earthquakes, a near-constant background hum of seismic activity that gives scientists a rich, continuous data set to study. Cascadia does almost none of that. It sits nearly silent for centuries at a time, which is exactly what makes it so hard to read and so unsettling to monitor. Researchers have openly admitted that this offshore silence is one of the greatest blind spots in American earthquake science. The regional cabled array, and the tremor data now pouring out of it, is the first real attempt to fill that blind spot in, and increasingly it is filling it with warning signs. The picture becomes sharper and stranger when you look north to Vancouver Island. In the fall of 2025, a separate team of geologists, using data from an ambitious offshore imaging survey known as the Cascadia Seismic Imaging Experiment, published findings describing something that had never been directly observed before in this fault system. A massive section of the Juan de Fuca Plate, torn apart, with a slab of oceanic crust that had dropped more than 3 miles relative to its surroundings. Geologist Brandon Shuck of Louisiana State University, who led that study, described it in stark terms. For the first time, scientists had a clear picture of a subduction zone caught in the act of dying. The tear has not sliced completely through the plate, but researchers say it is close. A dying subduction zone does not mean a safe subduction zone. If anything, the opposite may be true in the near term. As a plate tears and fragments, stress does not simply vanish. It redistributes, concentrates, and can accelerate rupture in the segments still under load. Combine that with a rising tremor count, with fluid actively working through the fault's internal structure, with GPS stations recording the telltale backward creep of episodic slip across multiple segments simultaneously, and you begin to understand why seismologists who spent careers describing Cascadia as sluggish and slow are now choosing their words far more carefully. So, what are the actual numbers behind the fear? The United States Geological Survey estimates that Cascadia carries somewhere between a 10 and 15% chance of producing a full margin megathrust earthquake, magnitude 9 or greater, within the next 50 years. Oregon's own State Emergency Management Office has cited a slightly higher figure, closer to 37%, for a rupture of magnitude 7, 1 or greater somewhere along the zone in that same 50-year window. These are not contradictory numbers so much as different questions being asked of the same fault. And there is a third, more unsettling piece of the puzzle specific to the southern portion of the zone. Researchers say the odds of a partial margin rupture in southern Cascadia, magnitude 8 or below, are meaningfully higher than the full margin figure, and could arrive on a shorter timeline. None of these percentages are predictions of when. No instrument on Earth, cabled or otherwise, can currently tell scientists the day, the month, or even the decade a specific earthquake will strike. What the rising tremor count offers is something different and in its own way more valuable. A live physical signal that the fault is not dormant, that stress is actively moving through the system, and that the 326-year silence since 1700 has never meant nothing was happening. It has meant something was building. If the full 9.0 scenario were to occur, the consequences would not stay confined to the ocean floor. Modeling from Oregon's state hazard assessments describes shaking that could last 5 to 7 minutes along the coastline. An almost unimaginable duration for anyone who has only experienced a typical earthquake's 10 or 15 seconds of violence. Behind that shaking would come a tsunami capable of reaching heights of 100 feet in the most exposed coastal stretches, arriving in some communities in a matter of minutes, far too fast for a conventional evacuation. Coastal towns from Northern California through Washington sit inside that hazard zone. Bridges, hospitals, ports, fuel terminals, and emergency response infrastructure across the region were largely built before this hazard was fully understood, and retrofitting all of it remains a work in progress, measured in decades, not years. That risk is not confined to the coastline either. In a discovery that startled even seasoned Pacific Northwest seismologists, a research team examining fault structures beneath Seattle found evidence that a complex web of smaller, shallower faults running directly under the city may be considerably more active than previously believed. Cascadia has always been framed as the offshore threat, the deep megathrust looming somewhere out past the horizon. This newer research is a reminder that some of the danger may already be sitting directly beneath the region's largest urban population, closer to the surface, closer to home, and far less studied than the subduction zone that gets all the headlines. It is that combination. An offshore megathrust loading silently for over 3 centuries, a newly discovered network of local faults beneath a major metropolitan area, and a real-time tremor signal that is climbing rather than falling. That has pushed federal science funding toward this region in a way it rarely has before. In 2023, the National Science Foundation committed $15 million to the University of Washington, specifically to expand earthquake preparedness research, funding that has gone toward exactly the kind of offshore instrumentation now producing these unsettling tremor numbers. Kidoella and her colleagues described the next phase of that work as an expansion of early warning instrumentation across the seafloor, an attempt to buy the region something it has never had in its recorded history, seconds, or perhaps minutes, of warning before the ground beneath it moves. There is a useful, if uncomfortable, comparison sitting just across the Pacific. In March of 2011, off the northeast coast of Japan, a section of the Pacific Plate that had been considered relatively low risk by many seismologists ruptured in a magnitude 9.1 earthquake, producing a tsunami that overwhelmed seawalls engineers had believed were more than adequate and triggered the meltdown at the Fukushima Daiichi nuclear plant. In the years that followed, researchers going back through the pre-earthquake data found subtle signs of accelerating slow slip in the months before the rupture, signals that, at the time, were noted but not understood as a warning. Nobody is claiming Cascadia is following an identical script. Every subduction zone behaves differently, and Japan's dense onshore and offshore sensor network bears little resemblance to what existed off the Pacific Northwest, even 5 years ago. But Tohoku is precisely the reason American seismologists have pushed so hard for exactly the kind of instrumentation the regional cabled array now provides. The goal is not to guess the future. It is to make sure that if Cascadia is writing a similar sentence in slow motion, somebody is finally in a position to read it before the last word. It is worth pausing here, because it would be easy for this story to tip into pure alarm, and that would not be an honest telling of what scientists are actually saying. A rising tremor count is not a countdown clock. Episodic tremor and slip has been happening in Cascadia for centuries, most likely for as long as the subduction zone itself has existed. What is new is not the phenomenon. It is our ability to see it. The regional cabled array did not create this activity. It revealed activity that was almost certainly always there, hidden beneath a curtain of ocean noise that 19th and 20th century instruments were never sensitive enough to pierce. In that sense, this is not a story about the Earth suddenly becoming more dangerous. It is a story about scientists finally being able to read a language the fault has been speaking all along, And yet the honest, uncomfortable truth sits right alongside that reassurance. The tremor is real. The fluid migration accelerating fault, weakening is real. Published in a peer-reviewed paper, not speculation. The torn slab off Vancouver Island is real, directly imaged, not modeled. The elevated hazard probabilities from the USGS and from Oregon's own Emergency Management Office are real, calculated from centuries of geological evidence layered beneath the coast. Put those pieces together and what emerges is not a prophecy. It is a portrait of a fault system that has spent 326 years storing energy, and that is now, for the first time, being watched closely enough that its smallest movements can no longer hide. There's also a quieter, more human layer to this story that rarely makes it into the graphs and probability tables. Along the Oregon and Washington coast, communities that have lived beside this fault for generations have absorbed the science in their own way. School tsunami drills that children now practice the way earlier generations practiced duck and cover, hand-painted blue evacuation signs pointing toward high ground, bolted onto utility poles in nearly every coastal town, and a kind of practiced unspoken awareness among longtime residents that the ocean in front of their homes is not simply scenery. Emergency planners describe this cultural shift as one of the quiet successes of the last 20 years of Cascadia research, not eliminating the risk, which no amount of preparation can do, but narrowing the gap between what scientists know and what the public understands well enough to act on in the seconds that would actually matter. What happens next is, by definition, unknown. And every scientist quoted in this reporting has been careful to say exactly that. Episodic tremor and slip could continue exactly as it has for years, a slow, rhythmic release valve that never triggers anything larger. The elevated activity across multiple segments could ease as quietly as it arrived, the numbers drifting back down the way they have after past swarms. That is the scenario most consistent with 300 years of observed history along this coast. But history is also the reason nobody in this field is willing to treat the current numbers as noise. Every megathrust earthquake this fault has ever produced was, by definition, preceded by a period that looked, from the inside, exactly like this one. Quiet enough for people to go about their lives, and yet loud enough, in the deep and patient language of tremor, that something was already moving. To understand how unusual Cascadia's silence really is, it helps to look at the subduction zones that behave the opposite way. Japan sits atop a plate boundary that ruptures often enough that its population has grown up with earthquake drills the way children elsewhere grow up with fire drills. Chile's coastline has produced some of the largest earthquakes ever instrumentally recorded, including the 1960 Valdivia earthquake, still the most powerful ever measured. Both regions generate a near constant stream of small and moderate earthquakes, which sounds terrifying but is, in a strange way, a form of pressure release. Frequent small ruptures that keep the fault from accumulating centuries of stress in a single locked patch. Cascadia does not do this. It goes still for lifetimes at a time, which means that whatever energy is not being released in small earthquakes has nowhere to go but into storage, deep in the rock, waiting. That storage is not evenly distributed either. Geologists studying sediment cores pulled from the ocean floor off the Pacific Northwest have identified evidence of dozens of major earthquakes on this fault over the last 10,000 years. Some rupturing the entire 700-mile margin at once, others breaking only the southern or northern half. The intervals between these events are not a neat, predictable clock. Some gaps lasted only a couple of centuries, others stretched past 500 years. Cascadia has now gone 326 years since its last confirmed full rupture, placing it somewhere in the middle of that historical range. Not overdue in any strict statistical sense, but well within the window where the fault has ruptured before. Indigenous oral traditions along this coast preserved a memory of that last great earthquake, long before Western science caught up. Accounts passed down among coastal nations in Washington and Vancouver Island describe a night of violent shaking, followed by a wave that swallowed villages. Details that align with startling precision to the geological evidence unearthed centuries later. The sunken ghost forests, the sand layers deposited far inland, the tsunami records recovered from Japanese archives. When seismologists finally pieced together the story of the 1700 earthquake in the 1990s, they were not discovering something entirely new. They were confirming what had been carried forward in memory long before any instrument existed to measure it. That layered history is part of why the current tremor numbers carry so much weight in the scientific community, even though, on their own, they cannot predict anything. Scientists are not looking at 382 tremors in isolation. They are layering it on top of the torn slab imaged off Vancouver Island, on top of the fluid migration mechanism discovered through the regional cabled array, on top of newly identified shallow faults running beneath Seattle, on top of centuries of sediment evidence showing this fault has rupture cycles measured in centuries rather than millennia. Any one of these findings on its own would be a notable scientific development. Together, arriving within roughly the same 18-month window, they form one of the most detailed pictures of Cascadia's internal stress state that has ever existed. The Geodesy tells its own version of this story. GPS stations bolted into bedrock along the Pacific Northwest coastline have spent decades recording the region's slow, steady eastward creep as the Juan de Fuca Plate drags North America along with it, millimeter by millimeter. During episodic tremor and slip events, that creep briefly reverses. The ground relaxes backward for a matter of days before resuming its normal push. Watching that reversal happen at multiple stations simultaneously, spanning hundreds of miles of coastline, is how scientists know the current swarm is not a localized, isolated event. It is a signal moving through the fault system at a scale that has drawn unusual attention from researchers who track this region for a living. None of this changes what people along the coast are being told to do, which is, notably, not to panic, but to prepare in the same practical, unglamorous way emergency planners have been urging for years. Oregon, Washington, and coastal communities in Northern California have spent the last decade updating tsunami evacuation maps, adding vertical evacuation structures in low-lying towns where there is no high ground within reach of a fast-moving wave, and running public education campaigns built around a simple, memorable rule. If the ground shakes for longer than 20 seconds near the coast, don't wait for a siren. Walk to high ground immediately. Building codes for hospitals, schools, and emergency infrastructure across the region have been steadily revised upward to account for the shaking intensity a full-margin Cascadia rupture could produce, though officials openly acknowledge that retrofitting older structures remains years, in some cases decades, behind where engineers say it needs to be. The economic stakes embedded in that gap are difficult to overstate. Past modeling commissioned by regional planning agencies has estimated that a full Cascadia megathrust rupture could cause damage across Oregon and Washington, running into the tens of billions of dollars, with the true figure highly dependent on how much retrofitting has been completed by the time the fault finally lets go. Ports along the Columbia River and Puget Sound, critical to the entire West Coast supply chain, sit inside the hazard zone. So do interstate bridges, regional airports, and the undersea cable infrastructure that carries a meaningful share of the internet traffic moving between North America and Asia. A rising tremor count does not change any of those numbers today, but it is a reminder, delivered in real time, of exactly what is riding on a fault line most people only think about when a headline like this one appears. This is also why the funding flowing into offshore instrumentation matters so much beyond the science itself. Every additional sensor added to the regional cabled array, every new GPS station bolted into the coastal bedrock, extends the amount of warning time available if and when the fault does eventually rupture. Early warning systems already operating on shore across the West Coast can, in some scenarios, provide seconds to tens of seconds of advanced notice before shaking arrives at a given location. Enough time to stop a train, open fire station doors, or duck under a desk, but only if the sensors detecting the initial rupture are close enough and numerous enough to catch it fast. Offshore instrumentation sitting directly on top of the subduction zone, rather than onshore stations waiting for the signal to travel inland, is the difference between a 5-second warning and a 50-second one. That gap is precisely what researchers are racing to close. For now, the fault keeps doing what it has always done, just more visibly than before. The instruments are running. The regional cabled array keeps listening, every second of every day, 550 miles of fiber optic cable pressed against the seafloor like a hand against a chest, feeling for the next beat. The tremor catalog keeps updating, the count climbing and falling in patterns. Researchers are still learning to read in real time. Somewhere in Seattle, in Corvallis, in Vancouver, teams of scientists are staring at graphs that most of the public will never see, asking the same question the rest of us are only now starting to ask. Not if, not exactly when, but what is the fault trying to tell us right now? And are we finally listening closely enough to understand it before it speaks in the only language that leaves no ambiguity at all?